In this section, we introduce the idea of curvature. Now, curvature tells us how tight a curve is, or how fast a curve turns. So, geometrically, what this means is if we've got some curve that moves along like this section over here, the curve that doesn't have a whole lot of bend in it. So right here, the curvature, which we use the Greek letter kappa, is going to be small because there's not very much curve to the curve. There's not much turn to it. Whereas over here, as it starts to spiral tighter, the curvature here is going to be much larger. So the big curvature tells you the curve is turning faster. So to get to the idea of curvature, we've got to reintroduce some ideas you've seen before. And the first is arc length. So recall from 2 dimensions, you did this in Calc 2, the arc length of a curve was the integral from the starting point to the ending point of the derivative of the x squared plus the derivative of the y squared dt. Now in 3 dimensions, we do what might come natural. You just add the derivative of the z to this also, squared. So the difference between 2 dimensions and 3 dimensions is just the extra derivative of the z term. Let's look at an example of this. Let's take the helix. Let's take a helix who's given by 3 cosine t, 3 sine t, and 4t. So our arc length for this, and we'll do this on the interval 0 to 2 pi. So we've got the integral from 0 to 2 pi. Those are our starting t and our ending t of the square root. Now we've got to take the derivative of the first term, which is negative 3 sine t, and square it. We take the derivative of the y, which is 3 cosine t. We square it. We take the derivative of the z, which is 4. We square it. And then we're going to integrate this with respect to t. Now in here, we've got a 9 sine squared plus 9 cosine squared. By our Pythagorean identity, that's just 9. And then 4 squared is 16. So the square root of 9 plus 16 is 25, the square root of which is 5. So this tells us our arc length is the integral from 0 to 2 pi of 5 dt. We integrate this and we get 10 pi. So that's arc length on an interval. Piggybacking off that idea, we've got the idea of the arc length parameter. So to get the arc length parameter, we've got to have this arc length function on a more generic interval. So we're going to define the function s of t to be the integral from some starting point. By convention, this is usually we define this to start at 0, although you can pick any starting point, really. The arc length parameter is the integral from 0 to t of the same integrand. The derivative of x squared plus the derivative of y squared plus the derivative of z squared with respect to t. So if we look at this using the helix example from the previous problem, s of t is going to be the integral from 0 to t of, well, it's got the same integrand as before. So if we just sort of use the steps that we did previously, it's going to wind up as the integral of 5 dt. We integrate this and we get 5t. So that's our arc length parameter. Now if we solve this for t, we get that t is s over 5. So this is a way to reparameterize the original curve. So r of t was 3 cosine t, 3 sine t, 4t. To reparameterize this, I'm going to replace all of those t's with s over 5. So this becomes 3 cosine of s over 5, 3 sine of s over 5, and 4 s over 5. That's reparameterizing this in terms of arc length. Okay. Now with that out of the way, we're ready to actually define curvature. The curvature, which uses the symbolized by the Greek letter kappa, is defined to be the derivative of the unit tangent vector with respect to s. Now this is giving us a vector, so we're going to take its norm to give us an idea of how fast the curve turns. So this is the rate of change of the tangent. Now if the tangent is changing faster, we should have a tighter curve. If the tangent is changing slower, we should have less of a bend in the curve. So this is the definition of kappa. So let's do that on this arc length problem. We figured out what r is. And remember that the definition of t hat is that this was r prime divided by its length. So we go through, we've got r already. If we can use either version of these, we might as well just use the one with the s's in it. So we'll go through and take the derivative here. So this is giving us, for our r prime, we've got negative 3/5 cosine s over 5, and then negative 3/5, I have those backwards, this is negative 3/5 sine of s over 5. And then the next one, we take the derivative of that, we get 3/5 cosine s over 5. We take the derivative of the last term, and we've got 4/5. Okay, and we're going to divide this by its length. So we're going to divide this thing by the square root of, well, we take the square of the first component, so it's going to be 9/5 sine squared, plus the square of the second component, so that 9/25. So it's 9/25 cosine squared s over 5, plus we square the last term, we get 16 over 25. Okay, now down here we've got sine squared plus cosine squared. That's going to give us 1. And so the radical, just the radical part of this is the square root of 9/25 plus 16/25. And that's 25/25, which is 1. So this whole radical part actually, which is 1. So that tells us that our unit tangent vector is negative 3/5 sine of s over 5 and 3/5 cosine s over 5 and 4/5. So that's our unit tangent vector. Now we want to take the derivative of this with respect to s. So dt ds. So we'll go through and do our derivatives again. So on the first term, we've got negative 3 cosine s over 5, negative 3/25, excuse me. And the next term, we've got negative 3/25 sine of s over 5. And the last one, the derivative of 4/5 is 0. And now we've got to take the norm of this thing, because that's what the kappa was. It was the norm of the change in tangent. So we go through, we square the two entries, add them together, and we've got 9 over 625 cosine squared plus 9 over 625 sine squared, s over 5. And now the sine squared and the cosine squared again gives us 1. So now that gives us the square root of 9/625. And we take the square root, we get 3 over 25 for our curvature. So now if we've got a circle, this is an example in the book, but I encourage you to go through this on your own. If we've got a circle, the curvature of the circle is 1 over the radius. So this introduces the idea of an osculating circle. We'll get a chance to do some examples of this in class, but this is a quick overview. The osculating circle is kind of like a tangent circle. That is, it's got the same tangent vector as a curve. So in some sense, it approximates it well as far as the first derivative is concerned. It's got the same tangent vector. And it's got the same curvature as the curve. Now, generally, we're going to find the curvature in general, going through all the steps that we did in the previous problem, is usually a way to give yourself a big headache. Luckily, there's a bunch of formulas for curvature at the end of section 12.5, and we're going to use those extensively on this section. So we'll leave that it for now for curvature.